We're going to talk about something called polytopic LDI, and LDI stands for linear differential inclusion, right? So this is the system that we have: x dot equals a of t x, and this is not your run-of-the-mill ax, like typical LTI system, right? Yeah, this is not LTI, this is LDI, exactly. So one change of letter would cause us a lot of headaches, but in this case, this is a nice example. So a of t, right? So basically, this is not a constant, right? This a will not be a constant, and in fact, this will be like the worst case scenario. So what do I mean by that? This is convex hull, right? So a of t for a given a, a of t, that A matrix, that state matrix, will take values in this set, and then that set is represented by the convex hull of two matrices, and those matrices are given by this here, and A1 and A2. So let's imagine the case we have A of P x, and then we only have like one parameter, right? And then you would expect that, I mean, this is like a fixed parameter, let's assume, and P of t, that will stay constant, right? Okay, so this is the type of system, or let's imagine another case, and then in that case, let me get another color. So P is such a parameter, it takes values between P1 and P2, right? And let's call it P1, and then let's call it P2. So it can take any values between P1 and P2, right? So it can change like this, or it can change like this, or it can change like, slowly. However, it can do like every crazy action as long as it is in the set. As long as it takes values between P1 and P2, right? So in a way, we can talk about how realistic that is, but so you can imagine the type of stability that we would need to impose on the system will be pretty conservative. And so let's discuss this specific example, all right? And again, we are not putting any constraint on how A changes. We are just saying that A for a given T takes values takes values in the set represented by this convex hull of A1 and A2 given matrices. Okay, so let's look at the stability definition. No, wait a sec. So let's talk about this specific system more. And we have v of x. We have this Lyapunov function candidate, right? And just quick thing. So quick notation. X transpose px. This is square root, and then x transpose px. Okay, so this is like a shorthand notation. Instead of writing here x transpose p1 x, this is what we have. By the way, let me just say one more thing. And as you can see, this is Beamer LaTeX, and then brought to you by Overleaf. Actually, you know what, I'm not gonna do advertisements for them. I'm literally paying like $150 every year, and that is with the student or student option. So this is Beamer presentation. It kind of sucks the fact that you cannot make animations like you would make animations in PowerPoint. So, but other than that, when it comes to academic courses, like when you don't need to be creative and then do animations and stuff, Beamer is great. And I don't know, it has like this nerdy and then professional look to it. Yeah, at least thanks to ChatGPT and Claude. So I'm using them, and then I just wanted to have just one Beamer presentation or make one of my YouTube videos with Beamer. Anyway, that was like a tangent. So let's get back to that system. So this is called polytopic. Why is polytopic? This is because this is how we are defining. This is like some type of polytopic, right? And set that we are dealing with, and this is the Lyapunov function. Yeah, this is an interesting Lyapunov function, right? Yeah, why? I mean, we used to have, in good old days, we would have something like that type of Lyapunov function. Of course, anytime you have like a nonlinear system, it can get complicated and complicated. However, and this is the type of system that you can imagine. In a way, this is complicated, but in some other ways, it's not, maybe, right? Because, I mean, it looks linear, but it is changing. But it is changing or it has some type of structure, is what I'm saying, right? Okay, so the problem is, okay, we have this polytopic PLDI system, and then we also have this Lyapunov function, and then where P1 and P2 are given by this, and these expressions. So prove the stability. So this is, in fact, you know what? Analysis, right? What's analysis? You give me, I don't know, some type of system, like autonomous, of course, and or let's focus on the autonomous case, and we would find like v of x such that like some type of conditions are satisfied, right? Okay, so this is called analysis. In this case, this is like double analysis. Why? Because on top of the given system, we are also given like v of x. So, and then we are trying to prove if this is the case, if that given Lyapunov function would be enough to prove the stability for this system. So this is what I would like to call like double analysis, because of course in the future I will try to learn how we would go and then find such a v of x, because I am assuming like it might take some time, right? It is for me to learn. Hopefully I will learn, and then I will make another YouTube video. But yeah, let's be positive. And so the problem is that we are given this v of x, right? And this is the system. This is the candidate Lyapunov function. Come on, you can do better. And then that is also another reason why I try to strive for making presentations, because I know that my handwriting really is not great. So we're not gonna immediately talk about how this v of x would allow us to prove the stability for the system. There are some preliminaries, right? And we're gonna discuss them step by step. Otherwise, I'm telling you, like I can make a video in like 2 minutes, and then you wouldn't understand anything. It is, I'm always I have low expectation for my viewers. Why? Because I always consider my viewers as, I don't know, the type of people who would have the same intelligence as I have, and I consider myself as like a low intelligence person. So yeah, I will try to make it as clear as possible, because yeah, I would like to make a video that I would understand. So yeah, I have like low expectations, and because of my from my viewers. But I think this at the end, this is like a good thing for you. So right, sit back and relax, and then yeah, let's go through those like preliminaries. And as you can imagine, we have robust stability, right? And then of course after that, immediately we're going to talk about quadratic stability. And robust stability, we have this. What is this? For a given system, for all delta, right? Capital delta takes values from this set. Okay, so again, RS, robust stability, and this given system is robust, like robust is stable, and has the robust stability property if this basically state matrix is Hurwitz for all data in the set, right? Okay, so this is basic definition, but let's go to the LMI definition. We like LMIs, right? Yeah, who wouldn't like LMIs, exactly. And this is robust stability for an LMI definition. So again, this is the same set or state matrix for all data in the set, and is robust stable over that set. Okay, if for all data in the set there exists P. So if you remember, what was the, I mean, if you're like a total nerd or like someone who would like to do a PhD in control theory, what is the typical asymptotic stability definition, or like stability in the sense of Lyapunov? For all epsilon there exists data, right, such that when we start the initial condition inside this delta radius ball, this implies we will be in epsilon ball, right? For epsilon there exists data, right? Okay, and then here we're basically saying that, like, when you say for all and then after that immediately you say there exists, like this is like a kind of a cheat code. This expression is a type of expression that depends on the previous, like for all expression, right? So, and probably I'm sure like you've seen there are some definitions they explicitly write this. Why? We are saying that this delta depends on epsilon. So you give me epsilon, and then I'm gonna give you delta based on that epsilon, right? And that is the case. Okay. Anyway, this is like a stability ISF, like in the sense of Lyapunov. Let me just write it here. So this is basically similar to that. So what was the main point? Why I went through all this? Not because of my ADHD. I mean, probably because of my ADHD, but more importantly, for all delta, there exists P. So we are saying that this P is a function of this given delta, right? So you give me delta, and then I'm going to give you P, right? That is it. For example, let's imagine we have a parameter, and then this parameter takes values in a discrete set. Like it takes values between, or not between, it takes values from this discrete set, and it's like 1, 2, and then 3, for example. Literally the values 1, 2, and 3, right? And we need to find 1P, let's call it 1P1, and then P2, and then P3, such that, I mean, they need to be like positive, right? Plus, they need to satisfy that. Okay, and I'm just gonna write it. Let's call it A1, P2, P3, A2, A3, something like this. Yeah, by the way, one more thing. And this notation, so this is matrix, and then this is like S is in symmetric. Anytime you see that, that means X plus X transpose. Because in LMIs, this is the type of thing that happens, like you see like all the time, and then because of that they have like special notation for that, and that's why I wanted to also use. So that is the RS basic definition. Let's go to quadratic stability definition. So we don't have, I don't know, like a verbal definition or something, or implicit definition. We directly give LMI definition. So, oh my god, I made a mistake. No, wait, no, this is not. This is like literally robust stability definition. Okay, and then after that, yeah, I was trying to do some type of animation. Okay, so this is robust stability LMI definition, and then this is quadratic stability LMI definition, and this is crazy. Why? Look here. Like, we basically switch the places of those expressions, and then you are like, what would that correspond to? Like, what's the effect of that? The effect of that is huge. Why? Because this condition is way harder to satisfy compared to this condition, right? Because here I have huge, like great, tremendous flexibility. Why? You give me a delta and then I'm going to give you p, right? And here, however, I need to compute such a p that will satisfy the given condition in all the deltas from that set. Okay? Yeah. So it's like almost like, Lord of the Rings. And I'm trying to break the Nordiness record in this video, I think. So like 1p to basically loop them or satisfy all those conditions. Okay? And all the satisfy all of the conditions. And this is QS quadratic stability. Yeah. So let's again one more time. Robust stability, quadratic stability. However, the situation is that this is really conservative. And by the way, this is the only thing that you would use when you have a parameter and then you know that it is like fixed, right? So like also keep that in mind. However, if you have a type of system that's, you have parameter, let's say, and then it takes values between like minimum and maximum and like prescribed values, and you don't know, it would change, but you don't know how, like it can also change its values like in a crazy fashion, and you would need to, if you would like to have like at least some condition, like however conservative maybe, then you would go about using that stability or LMI condition problem. Okay, so what is this quadratic stability? Okay, I'm just giving another type of definition, and because we have this delta and then like basically the same. This is basically the same, and I have this intermediate definition and then theorem. Why? Because I'm just trying to make things easier, people, right? Yeah, I like how people or how my viewers appreciate that. So again, this is quadratic stability definition, LMI definition, and then we have this x at a of t, and where a of t again takes values in this convex hole. Okay, and then I'm also defining the sets, right? Again, 1 to n, and then I'm just defining set to make things easier for myself and then for yourself, for you as well, hopefully. And again, this is quadratic stable, right? If there exists p, right? And for all I index such that we have this condition. Okay, yeah. So instead of writing like the same thing n times, we have this shorthand notation, right? Okay, or we have this notation to make things easier for everyone. Okay, so quadratic stability. This is not basically quadratic stability. This is the theorem that you would use to make sure your system directly is not quadratic stable or something. I don't know. Wait a sec. Quadratic stability is a conservative like condition, right? A system, like rather that quadratic stability condition is a very conservative condition, and you would like to check if that like such a p doesn't exist in like directly, right? And so there's like another condition, so maybe that p directly will not exist, right? And basically for a given system, to investigate the non-existence of such p, you use that, and then this is the system definition, and then if there exists n, like like 1 to n, if r1 rn exists such that this condition is satisfied. By the way, I'm very confused right now. Like that ri, let me just check. Just give me 1 sec, okay? Wait a sec. This is really annoying. Why is it 86 or something? Oh, okay. I am so happy that I realized that. So, yeah. This is exactly. I was like, there must be some type of, like, what do you mean? RI, like, is it matrix? It doesn't make sense. Such that these RIs must be not even positive semi-definite. It must be positive definite. Okay. And then, in fact, let me just write it that way. Yeah. So this is so annoying, by the way. I mean, you put a lot of time and then you still, like, find out some errors. But I'm glad that we catch that. That was nice. All right. So if such RIs, right, a set of RI terms, such that this condition is satisfied, and then you make the claim the system doesn't admit such P, right? So basically, you directly say, you know what, the system is not quadratic stable, and this is nice to have. That type of theorem is like, and because you directly, if it is not quadratic stable, you would like to know that, right, before trying to figure out some type of P. Yeah. Okay, so that was like the, I don't know, like, first part of the preliminaries, and now let's look at the second part of the preliminaries. So S lemma. All right, first let's start with this strange definition. So Q for quadratic, by the way. Okay, we have this X variable, and then these are like the parameters, right? So this is the basically definition of that Q. I don't know, this expression. It's almost like quadratic. By the way, this is like what I wrote to make things easy for me. Like, I literally get this like S lemma definition from Wikipedia, right? So I have like crazy reliable sources. Okay, let me actually write source WikiLeaks. No, Wikipedia. I cannot spell Wikipedia anyway. So, all right, assume that basically non-empty interior assumption, and then the implication, which is, I mean, that is the implication that we're talking about, holds if and only if there exists non-negative lambda such that this expression is positive semi-definite. Okay, and sometimes you see stuff and then you're like, hey, it doesn't make any sense to me, and either you need to like study more, or the person who's like teaching is not doing a good job, or maybe doing a great job of scaring you. But in this case, I wrote it so you would get scared. Okay, so that's cool. If you're scared, that's great. But this is like, I don't know, like general definition or something. Yeah, this is like general definition. However, the type of definition that we will use, or I don't know, many people that I know, like personally, and like professionally and personally, right, socially, casually, they would use that definition. Again, you have this, let's say, quadratic term. Basically, I mean, this is quadratic term as well, but this is a simple quadratic term, and anytime you have that, let's say, situation going on, and then you may think that, where I will need this literally in 1 minute. In 1 minute you will need this. We're going to use this, right? I'm not going to explain it for no reason. And anytime you have this, let's say, relationship, or you have this situation, you can have that condition. And here's the like really important part. This is if and only if. So this is not like a conservative, right? This is not sufficient. So it's not conservative. This is like this is the best case scenario, right? Having if you don't know if condition, yeah, and there exists non-negative lambda such that this is satisfied. And here's the situation. Here you have, by the way, of course, you need to have like x in, I don't know, Rn, or yeah, Rn. We are getting rid of x terms, so this is easier. You can imagine, especially if you are dealing with like LMIs and you are trying to express the problem in a way that is optimization problem, and then hopefully it's convex too, right? So okay, so that was like the second part of the preliminaries. So this is the problem that we started. Now let's look at the problem one more time. For a given Lyapunov function, and then this is the system, we will try to show that this Lyapunov function can be used to guarantee the stability, asymptotic stability in this case. In this case, not quadratic, of course, or robust, whatever, but this is asymptotic stability, and for this given dynamical system. Okay, and this is PLDI, polytopic linear differential equation, right? Not DEI, like DI, LDI, okay? Linear differential equation, okay? So this is, by the way, it's very, like, I don't want to brag about myself, or I don't want to flatter myself like on air, but this is very nice of me to, like, even a simple, trust me, this is like a really simple like Python code, even the simple things I'm putting here. So you people, you people, and would have easier time to implement or something, or play with it, or think about it. And this is basically the set that we have, right? So why I'm talking about this set, like what's special about this set? Here we have this Lyapunov function, basically like maximum, right? So for example, if P1, that expression is greater than this expression, then the V of x that we have is this. And then what is V dot in this case? Then in this case, V dot will be I don't want to write it that way. I want to write it in a shorter way, hopefully. So P1. Also, I'm gonna write like a bar because I don't want to write a of t, right? By the way, a of t is, now that I talk about it, like a of t, like I don't want you to confuse it with this. This is like a of t is like a term here, but a of t is algorithm of thoughts. So it's like a crazy nice paper. I would like you to check it. Yeah, author is like a very smart guy. Sometimes can be annoying though, but let's move on. This is the V dots. This is V dots, and then we would like V dots to be negative, right? This will be our condition that we will investigate if that's the case. So let's get back to that first part, and then this set is important, right? And then here exactly this is what we are looking at. Right? So in this, like, I don't know, cyan or blue, whatever, or maybe turquoise or something, and this is the set that we are looking at here. And in this case, we need to look at, what was it? Yeah, P1. So V dot is right, is this, and then we will try to show if this is 0, like every point in this set. Make sense? And here, as you can imagine, in this, let's call it red region, the thing that we will investigate is this. Make sense? By the way, I shouldn't forget to put S symbol. Yeah, that's not cool for me to forget stuff like that. Okay, so let's move on. And yeah, this is like we have 1 and then we have 2, right? So this is basically 1, the first part of the state space. We will have two parts. And we basically divided the whole state space in 2 separate regions in a way, and then we're going to be looking at like 2 of them separately, right? So when we have that, this implies, and then this is, now you can imagine how we will use SLMA, or some things are coming into place, right? Okay, this is the situation, or if that is the case, then this is the condition that you would like to impose on the system, right? Okay, so, but this in and of itself doesn't look like the SLMA, I don't know, form that we use. So let's try to, manipulate it and then see where it goes, okay? And let's make things easier for ourselves. From here, we can directly go that, right? And then again, nothing changed here, like every change took place in left hand side. And after that, we from here we are writing this. By the way, like crazy simple steps. Like this is, I don't know, I don't want to brag about myself, but the fact that I'm showing stuff like that is like, yeah, you need to appreciate that, you guys, right, or you people. And okay, so now at this stage we are in a position to directly use the SLMA, okay? And where was the SLMA? Let's check. And yeah, exactly, look here, like, wait a sec. I don't think I can copy, but do you see how it is similar? Like some quadratic form, okay, less than 0, and again some quadratic form less than 0, and then there exists lambda. Okay, so yes, here, this is the left hand side. Some quadratic part less than 0 implies some quadratic part less than 0. And then if and only if, we have if and only if here, and we start with there exists non-negative lambda, right? Okay, cool. So, and what do? We take this expression here, and then we take this expression, and then we, subtract them, and the condition is that left hand side must be positive definite, semi-definite. Okay, so for the first region, that is the condition that we are investigating. And again, this is not a simple condition, but thanks to the people who work on the SLMA, now we have this condition. And here's the situation. So this A bar, and then there was the reason why I was denoting like or representing with A bar, right? Because A bar is not like a typical constant run-of-the-mill matrix. This is convex hull, like A1 and A2, right? And convex hull of those two quote-unquote points. In this case, the points are matrices. And okay, anytime you have a situation like this, we can basically write lambda 1, lambda 2, and then again, like copy and paste. We are copying and pasting, and this needs to be satisfied for, since this is convex hull, right? Let's say 1, 2, 3, 4. This is like a convex hull. Let's say A1, A2, A3, AN, and that condition needs to be satisfied for all lambdas. All right, okay. But here's the situation: we don't need to have like only one lambda. Okay, so there exists lambda. So in every let's say vertices of that, let's say geometric structure, we get to have like one lambda. It's not that conservative in a way, or that would be like crazy hard to satisfy. Okay, so these are the conditions for, let's say, a first part of the state space, that blue part, right? And that is the condition that we need to satisfy. And then here's the thing. In this case, we are lucky, right? Why? We have P1 and P2 given to us. And I mean, we are like in the problem, A1 and A2 are known, right? So literally, we need to find a non-negative lambda such that this condition is satisfied. This is like crazy simple, right? Okay, and again, like for lambda 2, we need to do like the same thing. And okay, that was like the first part of the state space region. Let's look at the let's call it this. Now it was a red, and now it's a pink. Yeah, pink region. By the way, let me just show it that way too. This is red region, and then this is a red region, right? Okay, so let's look at the red region, and here this is like the second part of the state space. Again, like P2 greater than P1, right? And then this is the condition that we are investigating. Again, we are taking the same steps, right? And again, using the S lemma, we have the situation. Since A bar is something coming from this set, which is given by a convex hull of those given like A1 dot 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 A2 points. In this case, points are matrices. From here, we can have these explicit LMI. In a way, this is LMI, yeah, and conditions. So this is great. Let's put all the things together, like all the conditions together. Again, this came from the first part of the state space region, and then like we have the state space, right? And then we divided by 2, and this is the first part. This is the second part, and we get those conditions from the first part, and then we get, or for the first part, and we get these conditions for the second part. And here's the thing, they are not like you don't see any x, right? So they don't depend on x. So this is crazy great for us. Okay, and we need to find like lambda. So basically the problem became turned into the following feasibility problem. So basically, let me write it that way. Find lambda 1, lambda 2, lambda 3, lambda 4 such that all of them are positive. And then these conditions are satisfied. Okay, so this is like a feasibility type problem, right? Okay, in fact, they are decoupled. Like we don't need to put all of them like together, like, right? We can have find lambda 1. Lambda 1 is like positive, definite, or like rather non-negative, and then we can have this condition, and we would call this like a feasibility problem number 1, and then we have 2, 3, and then we have 4. So this is it. Yeah, this also has like a nice structure in addition to the structure that we have. Okay, and the situation is that this is feasible for these given lambda values. And the source of this problem, of course, they were not like explaining like I was explaining, and I was explaining like as if I was explaining to like a child. And because I try to explain things like I am explaining to myself, and because I still have this like child in my brain, having fun over there. So this is the book, LMIs in Linear Matrix Inequalities in STEM and Control Theory. And Stephen Boyd, of course, this guy is like the legend, right? And then I'm assuming other guys are, legend for just being this guy's friend. Okay, by the way, that was a joke. I don't want people to get offended there. Of course, they're legends too, right? Okay, I think that is it. One sec. Yeah, I think that's it. There should have been like a thank you or something. Thanks for watching. Alright, don't forget to subscribe. And yeah, that's it. Thanks everyone, and don't forget to subscribe. See you.